Okay, good afternoon, and I appreciate the dedicated people who stayed this late. So this is joint work with Omer Angel from Vancouver, Sebastian Bubik, my colleague at Microsoft, and Fan Wei, student in Princeton who was an intern with us. And in particular, the slides are due to her, so give the credit. Um, so the problem is one of the most famous ones, max cut. And so I emphasize it will be weighted. So we have a graph with n nodes, and we have weights on the edges. The weights are arbitrary, so in this sense, the most general case is the complete graph because we're allowing all possible weights, and indeed we'll focus on thinking of the complete graph. But in general, there is a graph, there are weights on the edges, and the goal is to partition the graph so as to maximize the total weight of the edges across the cut. Well, that's a NP-hard problem, so one can make it easier in several ways. Most famous is approximation. Instead, we'll focus on finding a local maximum. And so a local maximum is just a partition where every vertex is happy where he is. If you move a vertex to the other side, you decrease the total weight, or at least you do not increase total weight of the cut. So while algorithms for max cut are problematic, I think everyone here, even in the current sleepy afternoon, can come up with an algorithm for local max cut. Please? Greedy, also known as flip. So choose a vertex in some way. If you can move it to the other side, increase the total weight, then do it. Otherwise, look for another vertex. If there's no vertex that you can move and improve, well, you've reached the goal. So sounds very simple. So this is what we're looking for, a local max cut. There's a before getting back to that, to the algorithm, I'll mention that problem of local. You might wonder, why do I care about local? One is, it's an approximation to global, but it's not the best method to approximate. There are several reasons we care about it. One is just as a paradigm of optimization, it's hard to find a global maximum. People often first find local maxima and try to have heuristic to find good local maxima. And there's also connection to Nash equilibria, where so in particular, a local max cut is so I already switched to the algorithm, but local max cut is a Nash equilibrium for the party affiliation game, where the weights represent a measure of distance, and everyone wants to minimize the distance from the individuals in the same group, which is equivalent to maximizing the distance from the individuals in the other group. So a Nash equilibrium for this party affiliation game, where you want to be in the same party as those close to you, is just the same as a solution of local max cut. So the flip algorithm is what was described as the greedy. There actually are many small variations you could make according to if you have many vertices who would improve, how do you choose one? You might choose the one that makes the biggest improvement. You might choose just a random one that improves. And so on. There are other heuristics as well. Now here's this surprising thing. On the one hand, there are experiments that represent what happens usually in the real world. This works very quickly. I'll come back to that. On the other hand, there are examples and that there are instances where it takes an exponential number of steps, and indeed this problem is what's called PLS complete, so it's complete in the class of local search. But maybe since we're focusing just on this problem, the most pertinent is there are weights that, and we'll only consider bounded weights here. So there are bounded real weights. You can convert them to very large integer weights if you want, but they're bounded real weights where it will take an exponential number of flips to reach the local maximum. So it's, you move a vertex, you move another one, and another one, then the first vertex is unhappy where he is, and you move it again, and so on. And perhaps surprisingly, this can go on for an exponential number of steps. So the tension here is clear. So we have these examples, but some people here actually run optimizations. Others, like me, have friends who run optimizations, and these friends often come to, and say, well, I have this optimization problem. I get stuck in local maximum. What can I do? Simulated annealing, something to find the global max. But you've never found like a real someone running a real optimization problem who comes to you and says, look, I'm looking for the local maximum. I'm running gradient descent, and it just never terminates. This problem doesn't occur in real life, but it does occur in these kind of extreme examples. So to settle this tension, that's where exactly, and what we do is actually very similar to the resolution current understanding of simplex algorithm, which is there are these hard examples, but typically, in the sense of smooth analysis, it's fast. But this has been known for some time for the simplex algorithm, and it's new for MaxCat. So, so the first thing also following, so actually in the simplest algorithm, the first thing that was done is look at just an average case model where the weights are coming from some independent IID distribution, and here, or the constraints or the coefficients, here in this problem for MaxCat, that was also open. So to show that when the weights are chosen, say, uniform in -1, 1, in IID, the simplest distribution, or you could take unbounded but Gaussian weights, which have some nicer properties in some way. Even in that case, it was open to show that it terminates in polynomial time, and it's still open to understand how long it really takes. So our bounds are still far apart. But beyond just this, so this IID case, the problem is that this is also far from any real-world example. So then a good compromise between the extreme worst-case examples that don't occur in real life and the IID case, which also doesn't represent real life, is case of smooth analysis. So you think of the weights are maybe worst case, but the resolution is not infinite. So no weight is known arbitrarily far. So the 6th digit, you think of it as random. So formally you model it as weights that are chosen in worst case and then perturbed, say, uniformly in a small interval around these initial weights. And that's what the weights that we are going to observe. So we're looking at almost worst case weights, but then allowing a perturbation in some constant size interval. So that's what smooth analysis is about, and I guess initiated by Spielman and Teng in this context of simplex algorithm. Now, there was already a breakthrough in this problem by Etscheid and Rugland in 2014, which say if you pick weights randomly or in this smooth way, so each one is uniform in some small interval, then the greedy algorithm, this flip algorithm, will be quasi-polynomial. So they prove an upper bound of n to the log n. And this is for any graph, and with worst case analysis of the flip algorithm. So even so each step you choose an improving move, but maybe there are some unfortunate improving moves that will force you to go for a long time. Well, they can't force you too long. It's bounded by n to the log n. And actually, Kostis Daskalakis showed us this proof and shared with us the feeling that their idea was so, I mean, the result is nice, but their method was even nicer, so it should be able to push it further. And we took up his challenge, and 3 months later, of attempts, we did manage to prove a polynomial bound for the smooth complexity of this problem. So that's what I want to sketch to you, but of course the main ingredient is to tell you the framework that Etchad and Rugland introduced, which we start together and then we part ways somewhere. So how many digits? Here it is. Okay, so assume the perturbation has a density bounded by phi, right? So if you perturb in in an interval of length 1 over 1,000, then the density will be bounded by 1,000 in that interval. Okay, and then so whatever length of interval you smooth on, the inverse of the length of that interval is this phi, because that's the bound on the density, and we pay a 5 to the 5th. So you really don't want to smooth an interval of length 1 over a million and rely on our bound. But of course, this is a theoretical bound. It's the first proof that this is polynomial. Let me jump to the end and say, many people performed experiments, including most of my co-authors, and they all agree that it's linear. So it's not just polynomial, it's linear, at least when you implement flip in any reasonable way. So we can't test the worst case implementation, but we can test, random and so on, and these are all linear. And so, the dependence on the density should not have any kind of fifth power. So
is this result still true if instead of randomizing it in an interval, you either add phi or you subtract phi with a flip of a coin?
So certainly not with our proof. So I can't. So I don't know. Yes. That's right. So. Yes. No, I'm trying to see, what's the first. Very soon we reach a roadblock for that approach. So how does one prove this? It is to divide time into blocks of length 2n, and show that in any such interval you'll improve by at least epsilon. So how many such blocks can you have? If you improve by epsilon, since the weights are bounded, there can be they're bounded, say, between minus n squared and n squared. So they only have order of n squared to increase. So only n squared over epsilon such blocks. So that gives you an upper bound of n cubed over epsilon steps. So we're going to prove this with epsilon, which is really n to the minus 12. And so that's where the n to the 15 bound comes from. I'm suppressing here the dependence on phi. Okay, so that's the idea, to show you cannot have a long block with tiny improvements throughout. One of them has to be, well, still tiny, but at least n to the minus 12. Okay, so just from this, you get the number of blocks to be at most n to the 14, so time is n to the 15. Okay, so the weights here are going to be some, as I said, some initial. The random weights will be some initial worst case weights plus some noise which has a density bounded by phi. This still has density bounded by the same maximum. And we can think of the cut as just labeling the vertices with plus and minus 1. So what happens when we move a vertex from one side of the cut to the other? The total weight changes by a linear combination of the weights involving this vertex and the other nodes, right? You have to So that's what is this linear combination. Alpha W is the change in weights that happens when you move vertex V from one side to the other. Okay, so the coefficients of the combination, so this alpha is either minus 1, 0, or 1. Now, just to keep the dimensions straight, so alpha is indexed by all edges of the graph. So since we'll be focusing on the complete graph, we're smoothing on the complete graph, so alpha has these n choose 2 indices, or its dimension n choose 2, but most of the coefficients of alpha are 0, because this alpha is at a specific time when a specific vertex is moved. So the configuration is now set, and it has coefficients only on edges that involve the moving vertex. So only n or n minus 1 edges have non-zero entries. Some of them plus, some of them minus, depending on the side of the other vertex besides the moving vertex. Okay, so that's alpha, right? So the VW coordinate of alpha will be minus sigma V sigma W when V is the moving vertex, and edges not incident to V get a 0 coefficient in alpha. Okay, so this is these alphas will play a role here. So the first observation, which is very easy, fix this particular vector, non-zero vector alpha of minus 1, 0, and 1. So just a deterministic vector, and ask what's the chance that for this particular alpha, multiplied by our random weights, that this will land in the problematic interval 0 epsilon. Well, if you add independent variables, the resulting sum is at least as smooth as any of them. So the maximum of the density cannot increase. So this sum has density bounded by phi. So we get this probability is bounded by phi epsilon.
So this is where my version will not work. Version of the problem.
Yes. Okay. Now what we'd like to say is, now let's look at the block of these 2n improvements. In each one, we have probability bounded by phi epsilon. So 2n of them, it should be bounded by phi epsilon to the 2n. And then we just want to do a union bound. So we have, so this, as it stands, is not true in general, because we ignored the possible and indeed existing dependence between these. But let's ignore this and just see where we'd like to go. So if such a bound would hold, we would do a union bound. We have 2 to the n initial configurations. The number of sequences of length 2n will be bounded by n to the 2n. Each time we have to choose the moving vertex. And then the probability of, so here it's a little tricky. We think of just one initial configuration, but to get this argument working, we really need to think of the initial configuration at the beginning of each block of length 2n. We want that all these configurations at the beginning of a block will be good. So that's why we are really taking it. We can't just say, let's stick to one initial configuration and that's it. We keep seeing more and more initial configurations are not at the very beginning, but at the beginning of a block. So we want that for any such initial, block initial configuration, the probability that there is some initial configuration, some improving sequence of length 2n, which improves where all the steps improve by at most epsilon. So we bound this 2 to the n, n to the 2n, and then this kind of fictitious hoped for bound. But if we had this, then just taking actually epsilon to be here constant over n. So this wrote constant over n squared, but you don't really need that. Just constant over n will be enough to get this probability small. Okay, and then once this probability is small, we can just iterate. So, of course, the problematic thing is this. Um, so we have these alphas, which I'm writing as column vectors now, one for each time step, corresponding to the moving vertex and the current configuration. Now, this possibility that two are equal can't arise in the complete graph, but linear dependencies do arise. So if I have, for instance, one vector, one alpha that's the sum of two others, then this very rare event becomes not so rare, right? If I know that alpha 1 that alpha 1 times the weights is small and alpha 2 times the weights is small, so let's say less than epsilon, then for the sum to be less than epsilon is constant probability now, not like epsilon. So linear dependencies really hurt that probabilistic calculation. Now remember, I told you I didn't give you the sequence, but I told you that there are examples of weights where you keep improving for exponential number of steps. So, so that means you keep having all these alphas that correspond to improvements, and there are exponentially many of them in a space which is just n squared dimensional. So you can get a lot of linear dependencies. But that's really... Yes, these are dependencies over the real. So this is part of the dependencies figure in this probability calculation. So let me say the place they come in is that this is really the issue. So if these vectors, so these alpha 1 to alpha k, so these are -1, 0, 1 valued vectors, if they are linearly independent, then you are fine. It gives, so linear independence in this case gives you the statistical independence. And so this is a lemma. It's basically just a Jacobian change of variables lemma, relying on the fact that all the alpha coefficients are all integers, and then you can write, the Jacobian matrix involves just integers. So you get that the probability that alpha iw is in an interval of length epsilon for each, it doesn't matter where this interval is, the probability that this happens for k steps is indeed bounded by phi epsilon to the k, provided these are linearly independent. So the game is to find linearly independent ones. Or in other words, to estimate the rank of this matrix. But we'll see that just estimating the rank will not be enough. More tricks will be needed. They already were devised, some tricks were devised by Eschheid and Rugland. I'll come back to that. So, okay, so if we can repeat the same thing with the rank of the sequence, in particular, if you were in a good situation where somehow your block of length 2n had really order n, rank of order n, then the same argument from before would work, slightly different constants. So the problem is, what we can say about the rank. Okay, so this is an example. I don't know how informative it is. This is an example where these 5 vertices are moved in order, and alpha is written in the columns in each column. Remember, this is the index of alpha is a pair of vertices. So say if v1 is moved, then the only non-zero entries here correspond to edges that involve v1 and so on. Okay, so some parameters that will come in the calculation. So it will turn out that it won't be enough to just work with these blocks of length 2n, because if the rank is much lower than 2n, we'll want to focus on shorter subblocks. So given a shorter subblock b, L of b will denote its length, and S of b will be the number of distinct vertices that occur in the block. Okay, and here's a simple rank lemma that says rank of b is basically at least S of b, so you can lose 1 if all the vertices are moving. So this is straightforward. Maybe you'll see it. So I'm saying the rank is at least the number of moving vertices minus 1. And if not all vertices are moving, you don't even need to lose the 1. So for instance, in this, so you can see this clearly in this example. So in this example, V4 is not moving. So we're just going to look at the moving vertices, and each time look at the coordinate corresponding to the moving vertex and V4. Well, for each single vertex, that coordinate is appearing just once. So there's nothing. So once we have, so this V1 is moving. If we are, so here it's occurring twice because we're looking twice at V1. But if we just take each moving vertex and take it just once, then we obviously get linear independence because we take here the moving vertices V1, V2, V3. These three independent rows imply that these three columns will be independent. So okay, so as we said, if the rank is linear, we are good. And the problem is that the rank could be much smaller. So for instance, square root of the length of a block. And then, I mean, this is written out here, but the argument breaks down if the rank is, if the bound for the rank that we can give is so small, just the square root of the length. So here is where the yeah, you cannot get, it's on the complete graph, you cannot get repetition. So it cannot be extremely small, but that's right. But already square root kind of kills the argument as I describe it. And I mean, the key thing that kills it, maybe I can emphasize it, is this factor of 2 to the n. So this is one problematic factor, 2 to the n on the initial configurations. Because if you look at a shorter block, you can deal with some of the other factors. So if you look down here, where is this? So, so there are the factors for which vertex is moving each time. If the block has length L, this is just n to the L. So this is actually can be quite benign. And then we have phi epsilon to S of L. So suppose we find a shorter block. By shortening the block, we can certainly make the number of vertices that move in the block half the length of the block. Because shorter and shorter, eventually, length 2, it's going to hold. So we can make S of L to be the same order as L. And once we have that, then these two factors, we can balance them nicely by choosing epsilon, less than 1 over n. But if we make the block too short, this 2 to the n is going to kill us in the front. That's really the bane of this proof. And the way Etzai and Rugland dealt with that is by looking only at vertices that move twice. So if you look at the vertex that move twice, take these two alphas that correspond to say the first two movements and add them up, then all the non-moving vertices cancel out, and the only thing you have to worry about is the moving vertices in the block. And hence you don't need to do this enumeration of 2 to the n, which was the initial configuration of all the vertices, because the non-moving vertices you don't care. They're canceling out. You just need to enumerate over the moving vertices, and that's that was their idea, and that helps a lot. The problem with that idea is that the vertices that are moving twice, their number might be small in all blocks. So there are configurations where in every block of length L, the number of vertices that move twice is L over log n, and no more. And on the other hand, that's the worst case. So one thing they proved is that you can always find a block of length L where a proportion at least L over log n of vertices moved twice or more. So then they could use these, and that log n loss translates in the end to the quasi-polynomial bound. That L over, so that L over log n meant to deal with this, they needed to make epsilon to be not 1 over poly, but 1 over n to the log n, and that's where they got the result. And this is the, if you use this method using the vertices that move twice, that's as good as it gets. So what we're doing is dealing in a different way with this 2 to the n configuration bound. So we don't, so again, enumerating the number of moving vertices can be small, can be just square root of the length of a block. So enumerating over all of them is deadly. We don't want to do that. But we have to figure out that the moving vertices, the non-moving vertices, we don't want to and we don't need to enumerate over their states because we can lump them together. So if you look at any vertex that's moving, when it's moving, it doesn't care about the individual weight with each non-moving vertex. It can lump them together. So this lumping together means that you just need, if S of B are the number of moving vertices, these are important. You have to enumerate over their initial states. And then you also have to enumerate over the effect of the non-moving vertices. So what is that effect? So they have a separate, different effect on each moving vertex. So that's this S of B power. So for each moving vertex, we're going to lump together all the non-moving vertices, weights against it. And this lumping will lead to a total weight, which is, well, at most 2n. And since we care about things at resolution epsilon, we're going to do a pigeonhole. We're going to divide this weight into bins of size epsilon and ask, for a given moving vertex, its total weight against all non-moving vertices, in which bin does it lie? We want to enumerate over that. So this is 2n over epsilon possibilities to the power of the number of moving vertices. So this basically replaces in the union bound this with that. And that's one kind of key idea of the improvement. Then the really hard work, as we'll see, is getting a better bound. Well, I won't show the details. We're getting a better bound on the rank. But so this, so I said, so the new union bound has this 2n over epsilon to the S of B for the quantized lumped weights, and the 2 to the S of B for the initial states of the moving vertices in the block. Okay, so now when you write out what this gives, so maybe what's the clearest way to see this? Okay, so there is this size of the moving set, but just fix some size, S of B, and then what factors do you get? So we said you get 2 to the S of B times this. This is the new enumeration that we just discussed. Then we still have S of B to the power 2S of B for determining each of the moving vertices. Where are they? Each of the moving vertices, in what order are they moving? So at each step, so the length of the block will now be 2S of B. So in each of these 2S of B steps, which of the S of B vertices are we choosing? So that gives us this factor. And then we have this phi epsilon or 2 phi epsilon to the power of the rank as before. So when you look at this, you see that epsilon is, before it occurred just once, but now it occurs twice. So epsilon is taken here to a power S of B, but it's 1 over epsilon. So this is a big thing, big number. And here epsilon to the rank of B is helping us. So to get something from this argument, we really need rank of B minus S of B to be substantial, and substantial enough to deal with the remaining factors. It really needs to be of order S of B. So we had the trivial bound. Rank of B is at least S of B. We need to improve that trivial bound, and that's and that's kind of the heart of the paper, which you probably will have to look at the paper to see, which is that we have a bound. Rank of B is at least 1 1/4 S of B. So this relies on a more careful analysis of vertices that move different number of times, and so we can't just use the vertex the first time it moves. We have to somehow use later times to increase the rank. And this is what we were. So this is most of what the 3 months were spent on, was dancing around this goal, feeling, we almost had it for the last 2.5 months of those 3 months, but it kept eluding us. But finally, so we have this. This is the key bound. So is this a tight bound? I don't. Yeah, I don't know. I think we had some examples where it's only 1.5 S of B, but I'm not sure if there are examples with 1.25. As far as the proof goes, there's no difference here if it's, I shouldn't say it's no difference. It actually does change the degree of the polynomial. So the degree of the polynomial turns out to be 3 over your gain compared to 1. So we get plus an extra 3 for overhead. So that's what gives us the 12. The 0.1 is just for show. It's really 12, and so what we get for 12 is 3 over 0.25. So if you prove it to 0.5, you'd get 6 and final result of a 9 or something. But remember, it's really a linear thing. So I'm going to not go through the details of that, but the paper is on the archive with those details. And I can tell you, one of my co-authors did try in a talk to present all the details. And this is a result of some adaptive learning that maybe that's not the right thing for a talk. And so I'll conclude with two conjectures. So the most interesting one is just to show that on the complete graph, maybe on any graph, the smooth complexity is order n, maybe with logs. But now one obstacle here is we don't have any way right now to distinguish between a good flip algorithm and the worst flip algorithm, right? So this bound of n to the 15 works against an all-knowing adversary who makes us flip, who sees all the future and makes us flip the absolute worst sequence of improving moves. So there's no way for us to test what's the real performance of such a worst case adversary against a random or smooth instance. But who cares about that worst case adversary? Because we control the algorithm, we can just do. So it's just the nature of the current proofs that they don't distinguish a reasonable flip order from the worst flip order. So natural thing is the random, is actually the random one, because and so take a reasonable implementation, show that's order n. That's a big problem. Another problem, maybe more technical, is, remember I talked about the complete graph. So when you have arbitrary weights, of course, the complete graph is the most general. But in the smooth case, it's not the most general because I'm smoothing all the edges. So if you have another graph, you might want to smooth only the edges in the graph, not to smooth the zeros. But we're smoothing everything. And this is the same as what Spielman and Teng do in the simplex. They also smooth everything. And so that looks like maybe a more reachable improvement. So after those 3 months, we actually didn't release the paper for another month trying to get that, but we couldn't. So that's all. Thank you. Yes, Tim.
So on the last point, did you show us anything today which illustrated the difficulties in handling general graphs? Or is that all in your proof of the 1.25?
Yes, that's all in that proof. Wow. I'll have to do that offline. So it's and we can do that a bit here, and then when you get back to Stanford, catch Fan, and she can explain. But this is a tough technical point. Let me say that there are other cases. If the graph has bounded degree or even logarithmic degree, you can just do a union bound over all possible configurations. So, so the remaining things to worry about are graphs that are not complete but still quite high degree.
At least high max degree.
Yes.
So when you talked in the last slide about concrete ways how to implement the flip algorithm, you mentioned the random one.
Yeah.
But the more natural one is to make the biggest improvement.
Okay, we can. I think that one is more, maybe potentially more easily thwarted. So the random one, there's a paper of Luby et al. Which discusses in some settings why the random one is actually better than this best one, because so the worst one, so it's easier to create bad instances for the one that chooses. They know where you're going. Yeah, but anyway, in practice, the biggest one is a little bit better, but just by 20%. So they're all linear, and using the biggest improvement every step is a little bit better. But actually, if you go to the nitty-gritty of the calculation, right, there's some cost of finding the better one. So if you want to implement quickly, you would still go with the random one.